All right. So today I thought we would just go through like the very simplest of buffer overflows. Um, the idea is that there are like a bunch of mitigations in place nowadays, so it's actually almost like harder to do it like this. But this is just so that you get like a taster of what it's like, and then if people are interested, we can go through the more advanced mitigations, in a future session. So the like I guess for those who haven't like used C or don't really know what a buffer overflow is, it kind of all started with this paper by Aleph1, smashing the stack for fun and profit, and I guess that's when like the Morris worm and all that stuff came about. So before that, people hadn't really thought of the fact that memory that's user controlled can lead to like execution. So kind of a buffer overflow is about using more memory than you've actually allocated. So in C, you actually decide, you say, or in C++, you say, I know I need 20 bytes of memory, or however much amount of memory that you actually need. And then if you have a user that's malicious, they can decide to use much more than that amount. So yeah, kind of a buffer overflow, or even though you're actually talking about controlling execution flow, it's really about modifying memory in like very smart ways such that you can control execution flow. So typically when your OS starts a program, you start some executable on your machine. The OS is going to kind of initialize it using, there's like a huge there's a bunch of different things that go through here, but the idea is that once the program is started, it is like this image. So you kind of have your starting from the lowest address to the highest address, you have your text segment, which and like initialize data, BSS, heap, and stack. And kind of for this talk, the only thing that you really need to care about is the stack and how that interacts with your program. So typically, for those who haven't written C, the stack is comprised of the variables that you will use that only stay in scope when you're inside a function. And so like the stack, let's say you have a function which declares 2 integers or whatever, then those 2 integers will be on the stack. If you actually use like malloc or something like that, it actually ends up in the heap. And the lifetime of the stack is not managed by like manual things like calling free. It's actually managed by, the compiler will actually add instructions to your program that will free up and expand the stack. So this is, I guess this picture became a little bit bad quality, but the point is that when you enter a function, the function is responsible for, well, maybe it's clear like this. The function is responsible for 3 different things. It's gonna like push means add to the stack. So this, let me just clarify. What you see in this image right here is like the disassembly of a function that we're gonna look at later. So you actually see, these are the memory addresses these are not the memory. These are the opcodes for the assembly instructions. And this is the memory address on the total left. I'm hoping that you guys can actually see my mouse cursor.
Yep.
Yes. Yeah, cool. So so kind of this instruction, opcode 55, it disassembles to, push the current branch pointer. Like RBP is a abbreviation for like R, meaning that it's a 64-bit system, and BP for branch pointer. Pushing this onto the stack, the value that's in this register. Then finally, we're going to move the stack pointer is a separate register, move that to the current branch pointer, and then we're going to subtract 0x50, this is hex, from the stack pointer, meaning we're going to give 0x50 more bytes of space. So this is basically what's called the prologue of the function, expanding the size of the stack. And then we're actually moving some values. Sorry, we're moving the value of bar into some memory address. This is kind of the actual meat of the function. Don't really worry about this stuff. But finally, you get to the bottom of the function, you have these 2 instructions. leave does the exact opposite of the two instructions that you see right here. So this will add value back to the stack pointer and set the branch pointer to the stack pointer, and finally pop the branch pointer. And then finally ret, which is a special instruction, which will, so there's, in assembly, you have what's called RIP or EIP if you're on a 32-bit system. And this is the instruction pointer. This tells your processor exactly which memory address it should be executing code from at a given moment. And so ret, what that actually does is that it pops an item from the stack, and that item, it sets the instruction pointer to. So the address that it was in the stack now becomes the address that is the next thing that the processor will execute. This becomes, so kind of these things are very important for buffer overflows on the stack, because this is basically what you're going to manipulate. So if you kind of look at this, is now showing you the layout of the stack. You have at the very top of the stack, you have the local. So this is like the integers and characters and whatever you actually defined inside your function will be at the top of the stack. Slightly below that, you will have the return address. This is the address that, like, when you run the ret instruction from that you just saw a second ago, will get it will set the instruction pointer of your program to this address. And then at the bottom, you have the actual parameters. So this is if you have some function called draw line and it takes, say, 3 or 4 parameters, on x86 64 you usually use the registers for this. But if you overflow, let's say you have like 10 parameters that this function takes, then like the first 6, I believe, will go into registers and the final 4 will be passed as parameters on the stack. And kind of you chain together, if you think of like your like in Python, where you have a traceback, where you have several frames, you have the similar concept in C and C++, of course. And what that really is like a chaining of which functions it is that you're calling, so that when you open GDB or whatever, it can actually trace back these frames, as long as you haven't enabled too much optimizations, and especially when you have the debug symbols. And so because of that, GDB can kind of unroll, just looking at the current stack pointer and knowing where it was at the beginning of the function, it can unroll all these things and create like a backtrace for you. That's kind of just a fun tidbit. So yeah, prolog pushes current base pointer. I think we went through that. It assigns the value of the base pointer to the stack pointer, and then finally increases the stack pointer by, yeah. There's kind of like this really annoying thing, which is that, like, no matter, whenever you look at like a picture of the stack, as you saw here, the top of the stack being, I guess, the lowest value in this case, no, sorry, highest value is at the top, and then you'll have other pictures which will have the highest values at the bottom, so you're just always constantly confused. Epilogue, basically the exact opposite of the prologue. So the thing that we're basically going to exploit is the fact that in the epilogue, you're actually reading the return address from the stack. And so if you're some way able to modify the value that is on the stack, then you can change the value of the instruction pointer, as in the next function that your program will call. So the theory behind a buffer overflow with no mitigations is that you have some type of vulnerable function that's that does not do bounds checking, check that like the size of the thing is or that you potentially we won't get into that. You have some type of vulnerable function. You have a user input where somehow, because of the fact that it's user input, you can control the size of it, and you can actually make the max size bigger than the size that you've allocated. Once you send this thing, the stack gets filled beyond the allocated number of bytes, and after it overwrites the value of other locals, it can actually overwrite the value of the return address. When when the epilogue finally gets called, it runs ret, and that will mean that the user can actually control which function it will be running. So yeah, obviously buffer overflows are bad. because if you can actually control which function you're going to run, you are in full control over like the execution of the program. So if you imagine that this is running remotely and you have some type of attacker that's trying to get a hold of user data or whatever they're trying to do, it's bad. All right, so now for like a question for you guys. Based on what you heard earlier, do you have any idea what is wrong with this piece of code?
So we call the foo function with like 11 character long string, right?
Basically, we do not check the length of the string, right? Which means that we can copy whatever else is left, since
well, you're
like we say 12 character here.
It's
right?
11 characters, and then but you're copying in a 12 character array, right?
And if you don't put like a /0 in C, it's it doesn't. It means that the string is not over, which means that
yes, I guess
in
this case, when you call it like this, it's completely fine, right? Because you have 11 characters, and then there's going to be a null byte at the end, so that will add up to 12 characters. So like this, it's fine. But I guess what Chadi said is correct, that you're not doing any length checking. So if you wanted to, you could call foo with a string that's longer than 11 bytes.
Yeah.
And then you would actually be overwriting things. So obviously, this is just like an expanded version of the same thing, just with 64 bytes instead of 12. But yeah, it's the same issue. So if we were to run this program, I just called it BUFOV with like a stupid number of A's, we'd actually get a segfault. And does anybody kind of know why a segfault happens? Does anybody know like what causes segfaults?
It's when you're trying to access an address where you are not allowed to, because your OS basically gives you like an allocated like virtual space of memory that you can access. And if you access something like you're not allowed to, for example, the address 0 or anything else outside of this memory space, then it's just basically just gonna, get you out, and yeah, 6xV signal is gonna be sent, I guess.
Yeah, exactly. That's right.
But you're not allowed to write. The segfault comes from writing to unallocated address, right? But you can read from it.
No, it's
It's
both.
It's both.
It depends on the rights that you are allowed to have on the memory space, because you can set like permissions on your address space. Well, the kernel sets that for you.
Right. So both writing and reading.
You can even do that from your program. You can set permissions. Madvise can do that. You can set per page. You can set permissions. So you make a page. So I guess when your program starts, it's gonna set permissions on code segments that they're executable and this sort of thing. And so yeah, in this case, what's happened is that the return address got overridden with 8 A's, and so like 41, 41, 41, etc. And then when we tried to dereference the memory address 0x41, 41, whatever, it did not exist. So that caused the segmentation fault in this case. So what's fun now is that, I don't know if you guys have ever come across De Bruijn sequences, kind of just a non-repeating sequence of letters or whatever you want to choose. Just, you have a certain list of things that you want to create, and then you can create a non-repeating sequence of it. So these are super useful when you're trying to exploit buffer overflows, because you just often, of course, you can go into some type of decompiler and figure out exactly how many bytes you need to overflow. But in this case, it's actually more elegant to just send a De Bruijn sequence and then see when a segfault happens, you can find out exactly what the value was at that point. So in this case, we created the sequence, then we run the entire program with the sequence, and then we see that it failed at exactly the, at exactly the point SATA. So when we look for that, we see that that's at offset 72. So what happens is we had 64 bytes allocated for our buffer, and then there seems to be like one other address that's added. I'm not entirely sure what. Maybe it's the address of C itself, and then finally you get the return pointer at the offset 72. So basically, we know that if we're going to push 72 bytes of data, then we can push an address after that, which overrides the return address, and we know that because like there are no mitigations available, even like standard memory or the stack itself is executable. So we can do kind of like, this is what in this Smashing the Stack for Fun and Profit by Aleph One, this is kind of the approach that he always took, because at that point these mitigations didn't exist. And so we find out the actual memory address that this local buffer points to. So C points to exactly this address. And then we actually have enough already to build an exploit. So for those who haven't built exploits before, there's a tool called, or like there's a Python library called Poon Tools. That's fantastic. So, we can just pull down some very simple shellcode. There are lots of examples if you search for that. So this is shellcode that actually will spawn a shell. We set the values that we need for offset, set the memory address of C that we want to point back into. So this is where the return address will become this address. And inside that address will be this shellcode that we're pushing. Because kind of, if you go back to the original code here, what's happening is whatever we put in bar, the first 64 bytes of it will go in C. And then from then on, it's going to go upwards and up to the return address. So what that means is that at least as long as this shellcode is smaller than 64 bytes, we should be completely safe to just to change the return address to exactly the start of this, get it to execute this, and then you'll have a shell. Is kind of the idea behind that. Are there any questions before continuing?
How will you make the processor execute the code from the stack?
The processor will actually execute the code from the stack, exactly. So whatever is,
I tried to do exactly the same thing some time ago, but like my system wouldn't allow me to execute.
Yes. So what happens then is that you have what's called DEP, or data execution prevention. So we'll talk about that in like another talk if people are interested in this. But there are ways to get around that as well. Like we were mentioning, that like every single page on your system can be like, you basically have the three flags: read, write, and execute. And the entire stack is set to only read and write on startup when data execution prevention is enabled. So there's a GCC flag called -z exec stack, which will say that I want to make the stack executable. I want you to not run the code to make it non-executable. And from then on, everything will work. So let's do a little demo of this. So, okay, let's just do like so. I'll make this nice and big for everybody. All right, so I created this little disable ASLR widget. Let me just show you what that's just dead simple. Just a tiny bit of C code that just sets this personality thing, allows you to disable what's called ASLR, address space layout randomization, which we're going to talk about in potentially another one of these learning talks. But the idea is that what ASLR does is that it runs as the program starts, and it randomizes the location of the stack, the heap, and pretty much everything that you saw earlier. So let's also just like confirm the exploit looks pretty much exactly, what you saw earlier. You got your shell code, you got your offset, your address, and then of course you need some padding, because you need to make sure that the end of the shell code will be the return address, so that we don't just put that randomly. And typically, whenever you look at exploits, you'll often see that this value 0x90 is added in random places. And the reason for that is that 0x90 is actually remember how we were talking about opcodes earlier? It's the opcode for no op, or it basically just tells the processor to skip to the next instruction and not do anything. So if you ever then have kind of an off by one or something like that, and you just put a 0x90 in the right place, the processor will basically ignore it, which is exactly what you want when you're writing a exploit like this. So,
and I guess you can probably also disable it, right, when you're compiling the program by removing like alignment of functions, because I guess that's what you're trying to do here.
Yes, exactly. So the other part of this is that right now we have an extremely deterministic process because we know the exact addresses of things, and we can actually calculate the exact addresses of things. But in as we'll see in kind of other sessions, eventually things become more probabilistic because you're guessing addresses and you're guessing the values of things. And so then when you're able to say that even though you might be off by like 100 bytes or whatever, it doesn't really matter because the processor is just going to run over to some like a list of like 100,000 no-ops or whatever you do. So this is often what you do with heap spring, where you add a bunch of stuff where basically if the processor gets anywhere near it, it's going to be fine because it's just going to run down to finally hit your shellcode. That's the idea. So if we run this bad boy, this is okay. If we run it with like a stupid amount of A's, more than 64, we get a segfault, like we saw earlier. And if we then actually run it with, well, let's actually just run the exploit first so you can see that it's just like a random bunch of characters. If we now actually, oh, this is like a typical, it's actually this guy, isn't it? Or not? All right, this is like, well, in this case, this is a good chance to go into GDB and see what's actually happening. So right now, what we want to do is we want to break at the function foo. If you remember, foo was the name of this this process, and then we want to run it, and we want to give it the output of exploit. So now we can see this in practice. So basically, we can see now that we are at the beginning of foo plus 0 instructions. What we're actually going to do is we're going to step a few instructions, or actually we're just going to step forward a little bit, and we are going to break at this guy. So we're saying now I want the GDB to actually stop at this instruction. We then continue. Now we're at ret. So if we now look at the stack, we should see the, let's see. So the memory address that we have on the top of the stack here is this guy, 0x7ffdb50, and this should point back into our payload. So if we print the value of C, this is db70, in fact. So this is where the problem is, I believe. Okay, let's just, while we're doing that, let's, this is always like the demo.
Maybe when you recompile, like some of the address changed, like in the shellcode.
Yeah, that's exactly what I was thinking. So we're just gonna look at the.
It's weird, I guess, because it's supposed to be static from what you did.
Yeah, so this is here. You can see in the shellcode, it's address db50. So we want to actually do db70. So let's run it again. And then we're just going to continue. So let's see what happened now. So it actually got a breakpoint. Let's continue. And now we got an actual shell. So that should be right. Let's try to just run this again.
Seems to work now.
Oh, seems we're still getting a segfault. That's like the, so what I usually do at this point is that, so typically when you're running inside GDB, GDB kind of sets a lot of addresses, hard codes them, and puts them in like the way that you'd expect them to, or sorry, it puts them in a more deterministic way. But when you run it outside of GDB, you don't. So what's happening now is that like I just have like a single line get car in the process, and that just makes it much easier for us to attach GDB when we need to do something. Oh, I think I see what's up. So it looks like I actually have a program called, well, okay, what I'm gonna do is, before I even, I'm gonna edit exploit, I'm gonna set it back to DB50, and I'm just gonna run it to see if it was buff03, is the point. That is interesting. All right, well, that's not the thing. So let's go back to, well, I think the first thing I'm going to do is I'm just going to recompile this. Okay, buff03 is the like most recent one. Let's just, back to your point, Marcin, it's basically this -z XX stack is the one that's making the stack executable. And this one is also quite important to disable stack canaries. Yeah.
If I remember correctly, sometimes the system doesn't also allow execution of no-ops, right?
You said that again, Marcin? I didn't hear.
Sometimes you cannot execute no-ops in code. I mean, so when I don't know, probably by default, sometimes if you compile something, there are no-ops, because yeah, why would you have no-op in your code?
Yeah, so sometimes the compiler will do this for just purely alignment issues.
And basically, like your CPU, the way it works is that it tries to fetch stuff in advance before it's running, which means that sometimes it likes to have multiples of like 8 or like 16 so that it can load them into the cache. It's better to like align your code like this with NUP, which means basically you're adding like instructions that will pad. It's just padding, like you're doing on GPU when you pad sometimes your stuff, so that it executes faster. So it loads everything in those chunks, and then even if you execute useless information, it's usually way faster because you're removing IO bottleneck for compute bottleneck. So that's the idea basically for the snap.
Yeah, guys. So
David, by the way, what is a stack canary?
So a stack canary is actually kind of a genius mitigation. It's basically from this like canary in the coal mine is where it comes from. But the idea is that every time you run, let's say memcopy or any of these functions that potentially could overrun the size of your input buffer, what the compiler actually does is it adds an extra instruction before and after the memcopy, where before the memcopy it copies like some type of randomly initialized value to the end of the buffer, like right after the point where you would copy. And then after the memcopy is complete, it compares the value with like the known value, if that made any sense of what I just said. So that if you were to overwrite the stack beyond what you're allowed to, you would need to know the value of the stack canary and put the value of the stack canary to the right value. Otherwise, the program will segfold.
So it's kind of like a hashing salt, except like similar, right? It's just like has some random offset.
It's more just like a random value that you need to guess correctly.
Yeah.
So that's the idea. So, but this value only gets initialized at program start. So it after that it doesn't change. So there's actually quite a few problems with that. Like if you have a forking web server, this is like one of the typical examples where it's really bad, because if you have yeah, I guess we can go through that in like another talk, but like in a forking web server, since it only happens at program initialization, after a fork it will not get reinitialized. So that means that if you're able to make a request that somehow causes a buffer overflow, then that like sub-process will crash. But when the next fork happens and it like spawns a new worker, or however this program works, you will have the same canary. So which means that you can pretty much, if you're able to somehow override a single byte at a time, then you just need to guess 1 byte, of course, 256 values at a time. And if the value is correct, you can continue on to the next byte. So you only need to do 256 times 8 instead of like 2 to the power of what? Yeah, well, I guess 256 to the power of 8.
I see. So each process which gets forked off has just the same canary address, right? And,
exactly, it has the same randomly initialized canary. But yeah, that was way outside of this. But
That's
yeah, you see when we adjusted the addresses to the actual value of C, at that point you actually get a shell. So this is, if I run this with just some random values, it will, yeah, sorry, that was, of course I need to, it will just, well, actually, I guess this was less than 64. It will just crash. And if I run it with this guy, we actually get a shell. So that is kind of the entire demo.
so you executed your script basically, right, in the stack?
Yep.
Nice.
Let's see, can I not have that here somewhere? Why is he complaining about that? No such, oh. Yep. So that's demo time. And then how could we actually fix this? Like using things that actually can control the length of things much better. So you wouldn't copy more than is required. And usually like the man pages actually will tell you, so you can kind of search for these functions. Like never use this function is usually like a sign that it's not a good thing. And yeah, there's a bunch of replacements, and I think we've kind of already gone through a lot of these. So ASLR will, yeah, randomize the kind of base addresses of a lot of these things. Like the base address of the stack is now random instead of like being hard coded. That will make this exploit much harder, or potentially like impossible. You have to guess the value of the stack. Data execution prevention, which is what we were talking about, Marcin, that the stack is not executable. Stack canaries we also talked about. PIE, so like all code is relative, so you can relocate any part of the code to any other part. So, or sorry, not any part of the code, but like you can, everything is just, instead of having hard-coded memory addresses, you have relative addressing for everything. So you can actually initialize the code segments at different places. So you can't even use the code segments. And then finally, full rel-row, or yeah, relocation read only. So there are like, we probably won't get into these details, but like the process linkage table and the global offset table, they become read only. And there's a typical approach that when like things like DEP are enabled, you will just override a value inside the global offset table. And this is like a lookup table. Say you want to use like stir copy or something that's in like libc. This will get overridden with like basically a trampoline in the global offset table. So you can again override it with some code of your own choosing, is kind of the point. And that is it. Any questions?
So if you have all of these mitigations implemented, is there still a chance to run your opcode somehow?
Yes. So that is for another day. What I was thinking was, if there's interest in this, then I will go through, I'll probably make one for each of these guys, and how you can defeat it. And we'll probably just, for each session, we'll keep the previous mitigation enabled and just keep moving down the, probably we'll do stack canaries next, because that's the kind of simplest, or like ASLR and stack canaries, they are defeated in the same way. And both of those, like if you want to make it deterministic, the typical way that those are defeated is by having something that leaks an address. So like raw printfs are like a typical example, and raw printfs are really bad for several reasons, because you can also actually overwrite memory using a raw printf. So as in, like if you have a user controlled input to the printf, there are some special flags that can be used to actually overwrite the value of memory. So yeah.
That's pretty cool. I think you should do more of those, David.
Cool.